So what is the Hadamard gate? Hadamard 0, again, Hadamard 0, 1, 2, 3, up through n minus 1 if you have n qubits. Hadamard 0 is just taking two numbers a and b, and it's not flipping them, it's doing add and subtract. So it takes a and b, turns them into a plus b and a minus b. Sometimes you'll see people normalizing this and saying, oh, I'd like to divide those by square root of 2 so that I end up with the sum of squares ending up being the same. But okay, let's just not worry about the normalization and say a Hadamard gate is you take a and b, turn it into a plus b, a minus b. For instance, 3, 1 turned into 3 plus 1, which is 4, 3 minus 1 is 2. And 4, 1 turned into 4 plus 1, which is 5, 4 minus 1 is 3, and so on. Now, you can also do Hadamards at different distances. For example, Hadamard 1, that's at distance 2 in every group of 4. So instead of like not 1 was taking ABCD, turning it into CDAB. Hadamard, instead of just exchanging, is doing, well, it's taking both the positions that would have been exchanged, and it's doing add and subtract. So 3, 1, 4, 1, the 3 and 4 get added, turn into 7, 3 minus 4 is minus 1, and so on. And now you can put Hadamard together with other gates, and let's do some simple examples building up to something which is starting to actually do some kind of subtle stuff to the 2 to the n numbers. Let's start with some simple examples. Before any of the gates, then you would just multiply by 2 afterwards, so you wouldn't be able to, it doesn't interact with what the gate is doing. And the measurement, as I said, well, it's just scaling the numerator and denominator. You'd get the same probabilities of measurements. So this is something where none of the operations on a quantum computer can see this multiplication by. However, there is something which you could see later if you did more operations. If you were to measure right now the 6 minus 2, 8 minus 2, and so on, the probabilities of each result would be the same as a 3, 1, 4, 1, etc. But something has changed here, which you would be able to see if you did some more operations and then a measurement. And this is you've negated the b. The a and b turned into, aside from the factor of 2, a and b turned into a and minus b. All right, let's see if we can put together some more operations and start observing differences here. This next example is saying if index bits 0 and 1, so if the result after measurement bits 0 and 1 are set, then we're going to negate the amplitude, that position in the vector. Now, this operation, I'm going to assume that you're starting with a bunch of zeros. There's interesting data, 3, 1, 4, 1, but I'm going to assume that you also have 0, 0, 0, 0. In other words, if you were to measure, you get the Q2, the index bit 2, is going to be 0. Now, this is something which you can arrange inside algorithms, so it's not a big assumption, but it means you need an extra qubit to do interesting operations on the 3141. I'm going to use another qubit. And then with that, well, you see at the top of the diagram, there's a Toffoli, which is exchanging positions 3 and 7. And then there's a Hadamard at distance 4, Hadamard on qubit 2, which is, well, taking like 3 plus 0, 3 minus 0, 1 plus 1, 1 minus 1, etc. And that's basically repeating the 3141, except because of the Toffoli a moment earlier, instead of the final 1, we're getting a final minus 1. And then do a not 2. So this exchanges the positions at distance 4 from each other, and that moves the minus 1 into the first positions. Do Hadamard again. So this is looking like the previous example. What's happening here is, well, just negating that 1, turning it into a minus 1, and okay, also multiplying everything by 2. And then doing a Toffoli again restores having a bunch of zeros, the ancilla, the zeros at the end, and has turned the original distance 2, Hadamard on qubit 1. And so this is taking 3141. Again, I'm using an ancilla qubit, so having one more qubit, which puts a bunch of zeros onto the end of the data that I care about. And now the 3141, the Hadamards are turning those into, well, 3 plus 1 plus 4 plus 1 is the 9 I mentioned before. And then there's some subtraction, so the other numbers, well, you can trace through the calculations there, and get 9, 5, minus 1, minus 1. And now you negate the 9. So that 9 is at the first position, and you negate that. Now I put a ... there. This is not just one of the gates that we've seen. This is something which requires combining gates, as we've seen before. You can pick a position and negate that position. Well, okay, it's a different position from what we saw, so you have to change things around a little bit, but you can do that. Remember, we know how to rotate things, so you can move things between positions. And well, okay, just rotation is maybe a little bit slow to get through a big number of positions in the vector, but it's not too hard to jump quickly through by using strategic knots. And anyway, I'll leave that at average. And you can keep going like this and say, okay, can I do the following operation on my vectors? Can I change vectors as follows? And there's things you can't do, like you can't produce all zeros at the end. But there's lots and lots of things that you can do to these vectors. And these are the basic operations you can do in quantum algorithms. All right, this gives me enough background to show you Simon's algorithm. So Simon's algorithm is doing the following. It's finding a period of a function. What exactly are the rules here? Well, there's a function f, which you can compute efficiently. And this is something which takes n-bit inputs, which I'm going to call u, is the inputs to this function f. It's an n-bit string, zeros and ones, or if you like, an integer between 0 and 2 to the n minus 1. Now, there's also some assumption here, which is not something that you're given as input. You're given a program that computes f, but you're not given the next thing, which is s. S is a secret. S is a secret n-bit string, which we're trying to find. And then there's a guarantee as part of the assumptions, which is that f has s as a period. And when I say a period, I mean that if you add s modulo 2, as vector addition modulo 2, that plus in a circle, again, that's exclusive OR. On all of the n positions, you exclusive OR the bits of s to the bits of u. And if you make that change to the input, f gives you the same output. So that's an assumption. There's some secret period to this function f, where period is interpreted as addition of n-bit vectors modulo 2. One more assumption is that there are no other collisions in f. So when I say a collision, I mean two different inputs that give you the same output. And well, if there were more collisions, it would kind of spoil things. I don't want to get sidetracked by how that analysis works. So let's just assume all f is injective. It's one-to-one, except that if you add s modulo 2 as a vector to any input, you get the same output. All right, we're trying to figure out this s. Now, if you don't have a quantum computer, what you would do is say, well, okay, I try a bunch of inputs u to this function. I mean, maybe you look at the program for f and maybe it's kind of obfuscated, but maybe you can figure out what the secret s is by looking at that. But without looking at f, if you just say, somebody gives me the ability to evaluate f, then you would just try plugging in inputs, try plugging in some u's, and then maybe you find a collision. Maybe you find two different u's that have the same output. Now, this is something where you expect by the birthday paradox that after something like square root of 2 to the n possibilities, you're going to have some collision. Actually, this is a little more of an intriguing combinatorial problem here, that if you have a pattern in your u's that you're feeding in as inputs, how can you optimize that pattern so that you have like the smallest possible number of inputs u, so that they give you differences, possibilities for s, which are spread out as rapidly as possible across all of the possible differences s. You can try to make some pattern of u's that has many different differences, and then that would make this attack a little more efficient. But basically, the standard attack would be something like square root of 2 to the n possibilities until you find a collision. And then the difference of inputs is going to be that secret s. If you have a quantum computer, you can run Simon's algorithm instead. Now, what Simon's algorithm does is it runs f only about n times. Instead of square root of 2 to the n times, it's about n times. And then it says, here is the secret value s. So that's an amazing result compared to what you would expect to be possible. And there's nothing in this problem that sounds like you should be able to do that, but with a quantum computer, you can do that. All right, how does this algorithm work? Well, I'll show you an example where n is 3, and also the output of f is going to be 3 bits. You can imagine by the rules that the output of f could be only 2 bits, or it could be more bits. I'll have an example which is 3 bits, which are indexed along the top of this diagram, and 3 bits of input, 3 bits of output, which are vertical in the diagram. But okay, to say what the operations are. Step 1, you make a pure 0 state, a state which, if you measured it, would give you 0. And this is on 6 qubits. The number of input bits plus output bits is the number of qubits that you need here, plus any ancillas that you need to evaluate f. Okay, so you set up a pure zero state. This is a state where in the 64 positions, you just have position 0. How do you do that? Well, you take any state, you look at your quantum computer, you measure it, and it gives you 5. And then you say, oh, well, now I just do some knots and get back to position 0. All right, so now you've got your quantum computer as a pure 0, 1 just in position 0. And now you do some Hadamards. So Hadamard 0, that's taking AB, changing it to A plus B, A minus B. Okay, so the 1, 0 turns into 1, 1. And then you do Hadamard 1, and that's taking at distance 2, there were 1 zeros, which turned into 1, 1. And then Hadamard 2, and okay, that's all the Hadamards. So now you've got along the top, I'm thinking of the top as indexing input positions. Along the top, we've got all 1s, and then vertically, everything's in just position 0. Now, what's going to happen next is we're going to use this big vector processor to evaluate this function f on each of the positions separately. So the way to think about this is that we have 8 separate universes, 8 separate u's. And in each of those, at the same time, we're evaluating f on u and getting an f of u, which will be represented by the 1 is going to move somewhere vertically to the corresponding f of u position. Now, f has a bunch of steps in it for my example, and I'll just run through the steps. The first one is we do conditioned on qubit 0, we flip bit 3. So this is saying that at the odd positions, you exchange at distance 8, which is moving things vertically by 1 position. So at the odd positions, not on the columns 0, 2, 4, 6, but at the columns 1, 3, 5, 7, you move things. The not 3 is exchanging pairs vertically, and so that's exchanging 1, 0 to 0, 1. All right, and then you do another operation. And okay, I won't go through every one of these operations. This one, if you go back to previous and this one, you can think for a moment which operation is happening here. I'll just leave that as an exercise for you, is reconstruct which operations they are. Each one of these is just, I made a Python script which checked that this is really doing exactly a certain sequence of C naughts and CC naughts and such, and just knots. Okay, and so this happens for a while and stuff gets moved around. And then this was the end of the sequence of operations. And after this, something that happened that wasn't obvious if I go backwards, and then the ones were in all sorts of random looking positions. But at the very end here, suddenly there's exactly 2 1s in each of the rows that has some 1s in it. And those are at distance 5 from each other. And what do I mean by distance 5? It looks like maybe it's distance 3 up at the top there. But what I mean is if you exclusive OR 5, 1, 0, 1 into the input, then you get the other position of the 1. This function that's been evaluated in each column is periodic with period 5. So this is a surprise that you wouldn't expect looking at the program for the function f, that there would be this period. It's like it suddenly appears at the end that there's this period of 5. For example, if you take the column 3 and column 6, then 3 exclusive OR 6 is 5. And same for column 2 and column 7, those have exclusive OR 5. And so on through each of the rows that has a 1 in it. Now, Simon's algorithm does these operations without, it doesn't get to look at the 1s. It doesn't know that there's a 1 in these positions and then say, aha, here's the distance. But it's going to do some more operations and then measure in a way which is going to tell it something about this secret 101. We have this godlike view. Ganesha is looking at the whole computation and saying what's going on inside that quantum computer. But, well, for us running the quantum computer, we don't get to actually see what the positions are. So here's what Simon does to finish things off. First of all, there's a Hadamard again. Maybe I'll rewind for a moment. So this Hadamard is on adjacent pairs AB. Like the one on top towards the left, you see a 0, 1 pair there. And Hadamard changes that to 0 plus 1, 0 minus 1. So 1 minus 1. And same for all the other 1s or 1, 0, 0, 1 pairs in this. So the Hadamard changes that 0, 1 to 1 minus 1. I'm putting the minus on top of the 1 so that I don't spoil the whole alignment of this picture here. And then, okay, each of the zeros, 1s has changed into either 1 minus 1 or 1, 1, depending whether it was 0, 1 or 1, 0 to begin with. And then Simon does a Hadamard at distance 2 and at distance 4, and let's watch that happening. Again, you get the zeros and 1s turn into like all 1s or minus 1s, depending on the exact positions. And then, okay, depending, like if we look at the top again towards the left, then that 1 minus 1 if you take 0, 0, 1, minus 1, apply Hadamard at distance 2, then Hadamard 1 on qubit 1, so that's distance 2, then 0, 0, 1, minus 1 turns into, add those, you get 1, minus 1. Subtract, you get minus 1, 1. And that's what's happening on the top towards the left here is 1, minus 1, minus 1, 1. And same through the whole picture. And then Hadamard 2, so distance 4, and suddenly there's a bunch of cancellation. Suddenly, not every position is set. The first Hadamards at the beginning of Simon's algorithm, there were ones everywhere. But that's not what's happening at the end here. At the end, we only have half of the positions have some data in them. And then it's either 2s or minus 2s, depending on something about the pattern of where the ones were. And the vertical positions are, well, the function values that were taken, the possible f of u values, things were just moving along inside the rows. What happens if we measure? This is the last step in Simon's algorithm. Well, you get out one of these random values of f, and then what you get horizontally is only one of these 4 positions where you see a 2 or a minus 2. So you measure the 6 qubits, and the input qubits, the horizontal position, that's going to tell you either 0 or 2 or 5 or 7, one of the positions horizontally of the 2. Now that vector that you've written down in binary as a result of measuring these 3 input qubits, you throw away the 3 output qubits, that vector is something which I claim, you can check in this example, I claim it's orthogonal as a vector modulo 2. It's orthogonal to the secret vector 1, 0, 1. You can do a calculation of what Simon's algorithm does in general and convince yourself that, yeah, it's always going to be something which is orthogonal to 1, 0, 1. And also it's going to be a uniform random vector orthogonal to that. So whatever the secret is, Simon goes through this process and produces a vector orthogonal to the secret, which is leaking one bit of information about the secret. And then Simon just does it again and again and again until getting the whole vector space, and then it's just linear algebra to figure out what the secret is. Okay, n measurements, maybe you get some redundant vectors, but once you do n plus 10 measurements, you'd have to be very unlucky to not be done at that point. So Simon does basically n times evaluating the function, quantum evaluating the function, and then does some linear algebra very easily to reconstruct the secret. This is something that works for, again, any function which is periodic where, well, again, you have to worry about what happens if there's more collisions. But Simon is very reliable at figuring out periods of your functions if they are periodic. These periods have only been periods of, well, functions which are defined as like an input has a period when you add vectors modulo 2, take n-bit vectors added modulo 2. And this is where Shor came along and said, well, actually, you can do something very similar with more complicated addition operations. It doesn't have to be addition of vectors modulo 2. It can be, well, you have addition of integers modulo n for some much bigger n. Or actually, you can do just addition of integers in arbitrary ranges. Well, you have to think about what exactly a period means in that case in a way that you can represent with a finite number of qubits. But Shor, for example, takes a number n that you're trying to factor and says, let's take the periodic function that maps u to 2 to the u. This is something where I don't mean 2 to the u as a big integer, I mean 2 to the u modulo n. That's something you can compute quickly for a big value of u, and it wraps around at some point. There's only n different possibilities. Also, it's going to be, excuse me for a moment while I drink something. There's only n minus 1 at most different possibilities, actually fewer depending on how n factors. And then you take all those powers of 2, they're going to wrap around actually in a way that depends on the factorization of n. And if you can figure out what that period is, which is what Shor's algorithm does, then you can very easily factor n. Okay, if you get unlucky and you get some period which is sort of conspiring badly with how Shor actually does the use of the period, then maybe Shor's algorithm fails and he says, well, okay, it works with a significant probability, and then there's people came along and said, here's how you can increase that probability. But it's very, very reliable. I don't want to get into all the details of exactly what could go wrong. It is an algorithm that, when you do all the details, works with very good probability, and you can even increase the probability to basically 100%. Now, for discrete logarithms, Shor says, let's look at periods of a function with 2 integer inputs. So here, instead of just one integer u, there's 2 integers u and v. where those are, let's say, integers modulo p minus 1. P is some big prime number. And now you take the function mapping u and v as a pair to 4 to the u, 9 to the v, modulo this prime number p. And then that's again periodic. There's going to be periods, pairs s comma t, so that 4 to the u, 9 to the v is always the same as 4 to the u plus s, 9 to the v plus t. For example, one of the periods is you take s is p minus 1 and t is 0, or s is 0 and t is p minus 1. But there's more periods, and those other periods that are not just sort of obvious from p, if you have a random period, that will very likely tell you the discrete logarithm of 9 base 4 modulo p. And so this is what Shor's algorithm is doing to find discrete logarithms. Again, there's various details of how do you work with addition instead of exclusive or, how do you do the number theoretic part of factorization and computing discrete logs, but the basic quantum idea is extending what Simon's algorithm did, as we saw in this example a moment ago, to find a period of a function. All right, I'm thinking I'll do one more example, and then I should let people enjoy a break. And this one more example is going to be Grover's algorithm. So what does Grover's algorithm do? The assumption here is that you have a function. Again, imagine a function that's easy to compute. You have a program for the function, but secretly it has a root. And a root means, well, an input, an s, a 0 of the function. This is an input s, which you can plug into f to get 0. And there's, again, harder cases. I'll say something about those later, but let's just, for the moment, assume there's just one s, which is a root. So there's 2 to the n possible universes u, 2 to the n possible inputs u to this function. And you can, on a quantum computer, evaluate f in parallel on all of those. I mean, basically, Simon was doing that a moment ago. But, well, here we've got the problem of how do you identify just one universe sitting somewhere which has said, hey, I found f of u is 0. How do you get that universe to identify itself? So this is Grover's search algorithm. You've got a function f on 2 to the n inputs. You evaluate those on all the possible inputs. That's kind of easy. We've seen that once you've got these basic quantum operations. But where Grover's algorithm goes beyond that, beyond Simon, beyond Shor, is figuring out what S is, where it's just this one secret somewhere in the space of these 2 to the n universes. Somewhere in a list of 2 to the n numbers, there's a 0. All right. Now, this is harder to do than Simon's algorithm quantitatively. And it's harder for non-quantum algorithms. And also, Grover's algorithm will take more time than Simon or Shor. And we'll get back to the cryptographic consequences of that later. But let's first look at how you would solve this without a quantum computer. And then let's look at what Grover's algorithm does. If you have your laptop and a program for this function f, then, well, you just try plugging in some input. You try some u equals 0, u equals 1, u equals 2. Well, okay, maybe the function is not going to be nice to those first inputs. Maybe they were designing it to have the inputs later. So you start at some random point or maybe jump around randomly. So you evaluate f on many possible inputs, and then you hope that you're going to find the root. You hope you'll find the secret s. And, well, if you guess s, luckily, then good, you're done. And otherwise, you try something else. And of course, you don't want to do redundant guesses. Again, there's something to optimize here, which is easier than for the collision case, of just make sure that you don't try the same inputs twice. Now, if you try all 2 to the n inputs, of course, this works. If you try half of the 2 to the n inputs, that's the average number of tries, almost exactly the average number of tries that you have to try. If you have, say, 1/10 of that, you have a 10% chance. Okay, you can. It's interesting sometimes to think about, like, would an attacker try an algorithm that has a success probability of 1 chance in 1,000? If they have budget for it, maybe they try it. I mean, if it's something you can keep repeating 1,000 times, then you can increase the success probability up to basically probability 1. But suppose the success probability is like only 1 in 1,000, and then that's like all the resources the attacker has. Would they try it? Well, maybe. I mean, maybe it works. Do you feel lucky? Okay, so this is the best non-quantum algorithm. If you try, let's say, g different guesses, then you have a g over 2 to the n chance of success. What does Grover accomplish? Well, instead of 2 to the n, it's down to 2 to the n over 2, which was like, that was the cost before for the birthday paradox to find a collision. But now this is finding one unique s which has f of s being 0. And Grover does that in only square root of 2 to the n, which is, okay, it's not as dramatic as Simon's algorithm or Shor's algorithm, but it's still a big change. For instance, if n is 128, then 2 to the n over 2, instead of 2 to the 128, which is a very, very big computation, it's 2 to the 64, which is something that we could maybe do. Again, I'll get back to that later, the consequences of this for cryptography. It's certainly a big change in the numbers that you see, 2 to the n down to 2 to the n over 2. So what does Grover's algorithm do? Let me start this time with outlining the algorithm on one slide, and then I'll try a numerical example. So first of all, Grover sets up, just like in Simon, Grover sets up a uniform superposition over n-bit strings. So that means all of the amplitudes are 1. You have a vector of all 1s at all 2 to the n possible positions. We saw how to do that with Simon. You start with, well, you just measure, do knots to move to a pure position 0, and then do some Hadamards. And now you've got a uniform superposition over all n-bit strings. And now, step 1 of Grover's algorithm is to negate at certain positions in the vector. So you say the current vector is A, then you compute a new vector B and overwrite A with B. So what is the new vector? Well, it's simply you change A sub u, to minus A sub u if f of u equals 0. In other words, if u is the secret. And then if u is anything else, then you leave A alone. So we were seeing some of these examples before of, like, you can negate at a position if, for instance, the position is an even position, or you negate if Q0, you negate Q0 if Q1 and Q2 are set, or maybe I had it the other way around. But the point is, we've seen operations which are doing these negations by combining Hadamards and knots and whatever operations. You can build this operation as long as you're given a program for computing f. Then you can negate where f of u equals 0. Okay, that's step 1 of Grover's algorithm. Now, step 2 is called Grover diffusion, and this is negating A around the average. Hey, that's something we learned how to do before. So that takes the A vector, and instead of negating at the position where f of u is 0, it's negating every position in A around the position, around the average. So whatever the average of all of the A values is, you replace each A sub u with 2 times the average minus A sub u. And that's, again, something that you can do by combining operations that we've seen before. Okay. And then Grover just repeats these steps. So it's repeat, well, step 1, step 2, step 1, step 2, step 1, step 2, and do that about 58% of the number of times I was saying a moment ago. So instead of 2 to the n over 2, it's, well, it always looks much more scientific if you've got numbers with decimal points in it, even if you don't use scientific notation of 5.8 e minus 1, 0.58 times 2 to the 0.5 n times. So it's even a little faster than 2 to the n over 2. And then you measure. And the n qubits that you have for your u versus u, those are very likely going to be S, the secret. Now, it's not obvious why this works. This is something where you have to, well, prove it or try some examples. Let me show you an example, numerical example for a particular function f. We're going to graph the amplitudes. We're going to graph the a sub u as a function of u. U is going to go 0 through 2 to the n minus 1, and then a sub u is going to be vertical. And then we'll see what happens with these steps of Grover's algorithm. And then I'll say a little bit about how the proof works, that it works in general. So, all right, here's a graph of a sub u. And this is a normalized graph. So the a sub u's are all, well, I've divided all of the a sub u's by something so that the sum of the squares of the a sub u's is 1. And this example has n equals 12. So there's 2 to the 12th. There's 4,096 different u versus u, 4,096 positions in the vector. Now this graph might look like I have just an empty graph of a 0 function where for some reason I did range minus 1 through 1. Well, okay, range minus 1 through 1, if you have normalized numbers, the sum of the squares is 1, real numbers, not using complex numbers for anything today. If you have normalized numbers, so the sum of the squares is 1, obviously each number is between minus 1 and 1. So that's why the range is minus 1 through 1. And if you look closely at the graph, you see actually it's not exactly a 0 graph. If you have high enough resolution on the screen or on a printout, then you can look and see that actually each a sub u is slightly above 0. So there's a dotted axis for exactly 0. And then the a sub u's are 4,096 dots, which are at position 1 over 64 vertically. Why is it 1 over 64? Well, that's 1 over 2 to the 6. And if you square that, you get 1 over 2 to the 12. And then 2 to the 12 times that is 1. So the sum of 1 over 2 to the 64 squared over 2 to the 12 possibilities is 1. All right, so this is the normalized graph of A sub u, very slightly above 0. And now let's run step 1 of the algorithm. And what this is doing is it's at the secret position, it is negating f. So f was 1 over 64, and now it's changing to minus 1 over 64. And if you have high enough resolution, you can see that, the graph is dipping down to minus 1 over 64 at a certain position, which is the position of our secret. Now you run step 2. And what does step 2 do? Well, it negates everything around the average. So the graph was constant 1 over 64, except a minus 1 over 64, and then 1 over 64. So the average is just a little bit below 1 over 64. And then you negate around the average. So the minus 1 over 64 is distance, basically 2 over 64 from the average, and then it moves up to 3 over 3 over 64. And then everything else moves slightly because the average is not exactly 1 over 64. If I've said any 2 to the 64, what I mean is 2 to the 6. So 1 over 64. So basically, at the beginning, it was exactly 1 over 64. Then there was a negation at the secret, which made minus 1 over 64. And then negating around the average is approximately giving 3 over 64. And then all of the other positions are almost exactly 1 over 64. They almost haven't moved. All right, now step 1 is going to negate again. And that at the secret position is moving that 3 to minus 3. And notice that it's getting farther from the average. Like originally it was exactly at the average. And then the negation at this secret position moved to minus 1 over 64, which is 2 over 64 away from the average, approximate new average. And then the flip, well, same distance from the average. And now the negation, because it's negating around 0, it's farther from the average. So now we have minus 3 over 64, approximately. And then step 2 again negates around the average and goes up to basically 5 over 64. And then down to minus 5 over 64 and flip again. Okay, I've done step 1 and step 2 again, and step 1 and step 2. So instead of showing the flips, each time it's increasing by basically 2 over 64. Well, maybe a little bit less than that, but it's basically linear in the number of steps, how it's going from 1 over 64, 3 over 64, 5, 7, 9. Okay, and then keep going. And then, well, okay, after 20 of these repetitions, I'm going to jump maybe to, let's say, 5 more steps and 5 more steps. And then, okay, after 35 times these steps, which is, well, about 0.58 times the 2 to the n over 2. After this number of steps, now say measure. And what the amplitudes have turned into at this point is, well, very close to 0, except one of them is very, very close to 1. At the secret, it's very close to 1. And that means when you measure, you have almost 100% chance of, okay, it's not super close to 1. I mean, it's there is some gap there, but you have a very high chance of measuring exactly S. If it doesn't work, just try it again. And then each time you try it, you get another random chance of success. Okay, you could keep going. You could say, well, I'm going to do 40 steps, 45 steps, 50 steps. Now this, in Grover's original statement, he was really aiming for get really, really close to 1. So now it's like almost exactly, really, really almost exactly 100% chance. You can even tweak the algorithm a little bit so that you get exactly 100% chance if you have good enough control of your quantum computer. But well, there's no reason to put all this extra effort doing 50 steps instead of 35 for somewhat higher success probability. It's not as good as stopping after 35. And then if that works, great. If it doesn't, try again. Now you could keep going. You could say, I'll do 60 steps, 70, 80, 90, and notice things are going back down again. The average has gotten down, well, it's sort of moved, everything has moved slightly below 0. And then for the same reason things were moving up, they kind of moved down. And if you stop after 100 steps instead of 50 steps, then you have basically random output coming out. This is maybe even a smaller chance of getting the secret than getting anything else. So this is a very bad number of steps to do for the algorithm. And then you could keep going, and then it would get down to well, -1, and then you get to a good chance again, and etc. So it sort of cycles around some sort of circle between high success probability, none, high, none, etc. And that idea visually of what's going on with the probabilities is something that turns into a proof, which you can sketch as follows. You can say what's going on in Grover's algorithm by saying at each moment, this graph that we were looking at, there's basically the height of all of the non-secret numbers, all the a sub u's where u is not s, the non-roots. And then there's one height, which is the 3/64, 5/64, whatever the height is at the secret s. So there's just two numbers which completely describe what's going on inside this vector at each moment. You can simulate this algorithm by not writing down 2 to the n numbers, just writing down two numbers. And then those two numbers, of course, if you were to try to say where those numbers appeared on the original graph, you would have to know where the secret is. But for analyzing what the algorithm does, you only have to understand these two numbers. And then what do the steps do? Well, you can compute a matrix which says what happens to those two numbers. It's just a linear operation that happens to those two numbers when you apply step 1 and step 2. All of the operations that we're doing on these elements of the vectors, on the amplitudes, they're just some sort of linear operations. If you permute, that's a linear operation permuting entries of the vector, that's a permutation matrix being applied. Hadamard, the a plus b, a minus b, it's some sort of linear operation, the matrix 1, 1, 1 minus 1. And then if you do whatever composition of these operations, it's just some sort of linear map, which you can figure out what that does to these two numbers. And then you learned in linear algebra how to compute eigenvalues, at least with a traditional eigenvalues-oriented linear algebra course. You learn how to compute eigenvalues of a matrix, which tells you when that matrix, like how the matrix is rotating things through space. Of course, you have to be careful when you've got multi-dimensional eigenspaces and so on. But anyway, you use linear algebra to understand what's happening, what the evolution of these two numbers is. And then you end up concluding that, well, yeah, it really is rotating in a certain way where after about pi/4 times square root of 2 to the n iterations of this algorithm, the probability is, well, super close to 1. If pi/4 times square root of 2 to the n were an integer, you would get exactly probability 1 at that point. Again, it's good to stop before that. Also, it's not going to be an integer. So lots of reasons to not do exactly that number of iterations. But point is, you can mathematically analyze for any integer number of iterations exactly what the probability is of success, exactly what the a sub u's look like. And that's roughly how the proof of Grover's algorithm works. All right, I think this would be a good moment for me to say that people who are physically there should take a break and enjoy some nice milk tea. Again, I wish I were there. Sorry for not being there because of the circumstances, but I will restart in about half an hour. Let me look at my watch. So it's currently 25, and I think people should have their time for a break. So let's say I'll restart at exactly, I'm sorry, it's 25 in the time zone where I'm at, so it's 55 there. So we'll restart at 25, half an hour from now. Thanks for your attention.
So thanks, Professor Bernstein, for such a nice talk. Yeah, so we'll be having a small break of 30 minutes now, and then we'll be back for the rest of the session.
Okay, see you in half an hour.
Once the timer is over, the coffee break is over, Paulomi
So welcome back. Probably you have charged up after this tea break, and we'll be resuming this session with the talk of Professor Bernstein. So over to you, Professor Bernstein.
All right, thank you. So what we've seen so far is what quantum computers are doing. Whoops, flipped a little bit too far ahead. What quantum computers are doing as the basic operations. And then on top of that, we've built up from those basic operations to, well, all the way to Simon's algorithm, which is, okay, a little simpler than Shor's algorithm, but Shor's algorithm is similar to Simon's algorithm. And we've also built up to Grover's algorithm. And these algorithms have a lot of attention as like, these are the main reasons to be running quantum computers, is to be able to use, for example, Shor's algorithm, or, well, maybe to be able to simulate quantum physics. Now, the most important thing to appreciate beyond these algorithms is that there are many, many more quantum algorithms out there. It's not just Shor's algorithm and Grover's algorithm and simulating quantum physics. It's actually a huge number of algorithms, because every algorithm that you're using today, you can use as a quantum algorithm. Every non-quantum algorithm you can think of as a quantum algorithm. So the reason for that is as follows. If you think about what Intel is doing inside a CPU today, or whichever CPU you have, then it's really just a bunch of wires connecting a bunch of transistors. And these transistors are doing some bit operations. People will often talk about, well, the basic gates inside a CPU you're designing using, for example, XOR and NAND. At a very low level, NAND is somehow the simplest of those. But, well, in the end, you can boil down everything that your CPU is doing into just transistors are doing these very simple computations, gates on bits. And then every algorithm you're running on the CPU, well, in the end, it's just using those transistors, which are just doing bit operations. So whatever algorithm you're running today, you can use that algorithm as, well, just instead of thinking of instructions like working with memory or other complicated concepts, you can just do bit operations. That's really what the CPU is doing. That's how the electrical engineer thinks about, in the end, what's actually happening inside an algorithm, what's happening inside a program. Now, when you have a quantum computer, then you can take those bit operations, like an XOR, you can do an XOR using, well, a CNOT operation. And you can do a NAND using, well, okay, flip things around, but the AND is basically what a CCNOT, a Toffoli gate, was doing. And then the output that you get at the end, well, you can do that with measurement. Now, there's a little bit that's tricky here. When you do the simulation, there's a little bit different about a Toffoli versus an AND. If you think about an AND, normally you have some bits, say Q0, Q1 sitting there, and then you multiply those bits. That's an AND operation. And then you have a new bit sitting there. Now, Toffoli was a little bit different. A CC0 is saying we take Q0 times Q1 and then XOR it into another bit, Q2. And so you don't just create an extra bit, you have to XOR the bit into a bit that you have sitting around. But that's okay, you just make more and more bits for the extra operations. That every new bit that you want to create, you make another 0-bit, an ancilla, which you have sitting around, and then you XOR the AND into that 0, and now you have the result of the AND. So you can make your computation using new bits. You can turn that into a computation using these reversible operations like Toffoli gates, which are only XORing things into existing bits. You just have to start with enough bits to record everything that your computation is doing, which means maybe you need more qubits than your original bit operations. There's tricks to make that smaller. But basically, if you have a big enough quantum computer, then you can run everything that your current computer is doing, which again means you can take all of your current algorithms, non-quantum algorithms, and you can think about those as being quantum algorithms, which means that every fancy algorithm you might have learned for doing anything, that is a quantum algorithm that does the same thing. Of course, these are not interesting from the perspective of what extra things are we doing with quantum computers, because you can just do them on your current computers. But it does mean that your quantum algorithms are, well, including a lot of different algorithms, all the different algorithms that algorithm books are about. Even if they don't say the word quantum, they are still developing quantum algorithms that you could use on a quantum computer. Of course, because these algorithms are not using any quantum features, you should just run them on your current non-quantum computers, which are much lower cost. And then, well, you should also learn how to design these algorithms. If you want to be effective as an algorithm designer, then you should not just learn how do you do Shor's algorithm and Grover's algorithm. You should learn how do you do any algorithm. I mean, this is where computations come from, is not just, I mean, Shor and Grover in the big picture of all the algorithms out there. Well, Shor and Grover are important parts of that, but there are many, many other algorithm design techniques that are also important. And there are many computations where quantum computers don't seem to help. Once we have big quantum computers, then we're still going to be designing algorithms, which are algorithms designed in the traditional way, ignoring Hadamard gates. And just take your normal computer and then use that normal computer without thinking quantum anything. And then that gives the best algorithms that we know for many, many different problems. Of course, as illustrated by Shor's algorithm, if you want to factor a big integer, then it seems like having a quantum computer and using Shor's algorithm is the best way to do that. Also, for simulating quantum physics and various other problems, it seems like quantum computers using specifically quantum algorithms that are beyond non-quantum algorithms, that seems important for getting the best results. So as an algorithm designer, you want to learn both of these techniques to be able to see the fastest way to solve problems. It really depends on the problems, which of these techniques you're using. Are you doing something like Shor's algorithm and using these quantum operations, or are you just doing something completely non-quantum? That, again, often gives you the fastest algorithms. Many times, for a quantum computer, the best algorithms you can get are designed using quantum techniques like Grover's algorithm or Shor kind of techniques, along with using more traditional algorithm design techniques and even some fancy new algorithm design techniques that don't say anything about quantum computers, but then you can combine them with the quantum techniques to get better results. Now, Shor in 2001 was looking at the question of, is there really anything for quantum computers beyond the non-quantum algorithms that we know? Is there anything that's added except for Shor, well, including like Simon and Shor as one cloud of algorithms and Grover as another algorithm? And what he said was, these techniques for constructing faster algorithms for classical problems on quantum computers are the only two significant ones which have been discovered so far. Of course, significant is a judgment call, and he's ignoring, he has like one quick paragraph in his paper where he mentions, yeah, okay, maybe simulating quantum physics is also interesting, but significant leaves a lot of wiggle room to say what you're interested in. I should also say the word classical, this is not a good way to say, like if you have a feature of something like quantum and you want to say that, well, there's something else which is not quantum, then you would normally say that as non-quantum. If you say classical, then you're, well, confusing it with maybe other notions of classical. I mean, there's negative integers, there's non-negative integers. People don't say classical integers. This would get into disputes about whether the Greeks understood the concept of zero, that pretty much didn't. And well, anyway, point is, if you want to say non-quantum, say non-quantum. It's much less confusing than saying classical, which tends to refer to something which is older or maybe standard and not the new thing that you're doing. But classical problems can include very new problems that were not formulated before. What he means here by classical is non-quantum. Anyway, so he says that basically the Simon-Shor type of algorithm and the Grover type of algorithm are the only ways that you're doing more using quantum computers, using quantum algorithms, more than what you know how to do with non-quantum algorithms, which is, again, a huge important topic. Now, looking back at that 20 years later, it's certainly true that Shor's algorithm is important, and it's certainly true that Grover's algorithm is important. But you also have to look at more algorithms. There are many, many papers on quantum algorithms, and some of those actually are giving us the best algorithms that we know for some problems, which are more than just what you can do with Shor and more than what you can just do with Grover. So for understanding how quantum computers, quantum algorithms can do better than non-quantum algorithms, you should not just stop with, here's what Shor's algorithm does, here's what Grover's algorithm does. Let's look at some of the ways that Grover's algorithm has been extended. And some of these are not actually interesting, but some of them are really doing things that are more than what you can do with Grover and more than what you can do with just any non-quantum algorithm, any non-quantum technique. So let's go back to one of the things that I said about Grover's algorithm, which is you have a function which has a unique root. There's a unique secret s, and you're trying to find that s such that f of s equals 0. what happens if there are many roots of the function? It seems like it should be easier. If there's more and more roots, they should be easier to find. I mean, if you search through 2 to the n possibilities, that's overkill. If maybe there are 2 to the n over 2 roots, and then you would think if you just tried 2 to the n over 2 possibilities, that would be enough to find a root. Or in general, you would think that trying about 2 to the n divided by r, that would be about the number of tries that you have to do to find a root of f. Of course, if you think about it carefully, that's not exactly the right number, but it's close enough. I won't be super precise about the costs at this point. So, okay, if there are more roots, then there should be a faster search that finds it. In the context of Grover's algorithm, it's a little tricky to just say, oh, well, you keep searching until you're done, because you only measure at the end. And before that, you get this amplification, this particular amplitude flipping back and forth until it becomes big. If there's more roots, then, well, if you look at it carefully, then you see that, yeah, it does get faster, and you get one of those roots is showing up faster than you would get if you just tried the original algorithm for a unique root. But you have to decide when you're going to stop. So let's just assume you know what R is. Then you can, the number of roots of F. Then you can analyze exactly what effect that has by the same linear algebra, try some examples, you'll see that it works. And it does get faster. It's something like square root of the non-quantum search time. If you would normally spend 2 to the n divided by R approximately, then with Grover's algorithm stopping at a reasonable moment that depends on R, you would spend square root of 2 to the n over R time. Now, this is something where you can think about it as a slight variant of Grover's algorithm, simply choosing when you're going to stop the algorithm. But you could also say, wait a minute, I have Grover's algorithm. And Grover's algorithm, if you give me the ability to compute a function that has a unique root, then Grover you can view as a black box which finds that root in a certain amount of time. And given that ability, without thinking about any quantum stuff, without changing anything about how Grover's algorithm works, without reanalyzing it and generalizing the analysis, you can say, let's restrict the function. The function that we have with many roots, suppose we look at it on only some of the inputs. You just pick some random set of inputs. Well, how do you represent a random set of inputs? Maybe you start at this point and bounce around in a certain direction, or maybe you encrypt a certain set of inputs to make a pseudo-random set of inputs. This tends not to be a big deal to choose a sufficiently random set of inputs. And then you just try that limited set of inputs for a function restricted to that limited set of inputs, and then apply original Grover to that function. And that will work if there's exactly one root. And then, okay, so you can just use original Grover and thinking for a moment, how do I use that? And you get the same result. You get, if you think about it, the same square root of 2 to the n divided by R. That ends up being the performance of this just using Grover. You don't need an extension of Grover to do this. Now, you could say another common situation is that the function that you're producing is, well, something where you don't just want to know, is it hitting a particular value, like 0? But you want to know, is it hitting any of a certain set of good values? And there will be some function that you can evaluate, let's call it g, which recognizes the good values. And then you can again say, let's modify the quantum algorithm. Let's get into how this algorithm works, and let's have the f evaluation, which is turning into negating a sub q if f of q equals 0. Let's turn that into negating a sub q if f of q is a root of g. Well, you evaluate f of q, evaluate g inside your quantum algorithm, negate q if that is equal to 0. But this is really just doing the same as taking Grover's algorithm and applying it to g composed with f. First feed q through f, then through g. That is something that is a combined function, which you then apply Grover to that. So again, you don't have to rethink what Grover is doing. You just say, well, I'm applying it to another function. You could also say, well, this R, which I said a moment ago, let's just assume we know the number of roots of f, or in the generalized good situation, we know the number of roots of g of f. Then if you don't know R, then you could say there's some papers which are saying, well, you can estimate the number of roots using the following quantum estimation technique. And it's interesting, and some fun techniques go into that. But you also don't need it, because you can say, I'm just going to guess what R is. all of the analysis of how far you have to go in doing Grover's algorithm, you don't need to exactly know how far to go. If you're about right, then it's got about the same chance of succeeding. And if you don't exactly know R, then you'll get approximately the right probabilities. So you just have to guess some sequence of possibilities for R. You can say, well, maybe there's 2 to the n roots. Everything is a root. That would be very easy. And then maybe there's, I don't know, maybe there's 20% less than that, or maybe there's 20% less than that, or just try a sequence of guesses. And as the number of roots goes down and down and down, you have to spend exponentially more time to try these possibilities for, like, suppose there's only 2 to the 50 roots, suppose there's only 2 to the 40 roots, only 2 to the 30 is more and more expensive to try that. And for each of those guesses for R, you can try Grover's algorithm. Okay, 2 to the 40, 30, 20, that's maybe too big of the jumps, but you can, once you've gone through the original analysis of the original Grover algorithm, then without touching it, you can just use that and the probability statements for that algorithm and apply that to a reasonable sequence of guesses for R, and you end up with something which terminates at the right moment with high probability. It doesn't waste time. If you end up going 4 times farther than you should, then, well, you spent a constant factor extra time, but the chance of having to go much more is very, very small. Now, the next thing that I'll mention is something that is not known to be doable with just Grover. If you have Grover as a black box, that is not something which is good enough to do a quantum walk. So what are quantum walks doing for you? Well, the general situation is you have a function f, which is maybe not so fast to compute. You can compute it, but it takes some time. What you have that's fast is you can move from f of u to f of a modified version of u. So you define neighbors of u, neighbors of the input to f, as, well, a certain set of modified versions of u, such that you can quickly compute f of any of those modified versions. Given, I mean, you start with u and f of u and the modified version, so you see this little change to u. And then for any of those neighbors, the u primes, which are neighbors of u, any of those modified versions of u, you have an algorithm which moves from f of u to f of u prime. This is a very common situation. And then in this situation, you can, instead of saying, I'll make a random u, evaluate f of u, which is maybe kind of annoying, and then make another u and again evaluate f of u and keep piling up the annoying evaluations of f. What you can do instead is say, all right, I'll start with 1 value of u. I'll do 1 time, I'll compute f of u. And then everything else, I'll just move from u to a neighbor and that do the fast modification to f. Now, to get from the original u to any random u, and any random u prime, u double prime, etc., you might have to do many of these steps. So there's a certain mixing time, assuming that everything can be reached through moving from u to its neighbors. There's a certain number of neighbor moves that you have to do to get to any possible. And, well, you do that number of moves, and now you're somewhere random. And then you check, is f of u good? Is it, you apply this function g, which tells you, is f of u a good output, is u a good input? And then if it's not, then, well, you move again. You do more of a walk. So you move from the new u prime, 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 if that was the number of times to mix. Then you do another 5 primes, and then you say, okay, from that point, I'm now at another random spot, another random input. By moving from f to a new value of f, you move around through all the different u's. So you move enough to mix again, get another kind of random input, and then you again check if it's something good. Of course, if the checking for good, if that's very low cost, you can just do it all the time. But if it's a little bit expensive, then if f is kind of expensive and if checking for good is kind of expensive, but moving from f of u to f of a neighbor of u, if that's relatively cheap, then you can just sort of prioritize that inside your algorithm. Just move from u through neighbors, and now you've got a new pair u comma f of u for a new value of u, and then check if that's good, and so on. A quantum walk, whatever number of repetitions you do in this random walk that I just mentioned, where you have like this inner repetitions to mix, inner number of moving from you to a neighbor, and you've got the outer loop of how many repetitions do you need to get something good. The quantum walk replaces those repetitions by a square root. Now, in the case of Grover, this is a special case where, okay, you can think of what Grover's algorithm does as an example of this quantum walk, where you say your neighbors are, you've got a u and f of u, and we'll just define everything to be a neighbor of u. So you replace u by whatever random result, and you just recompute f of that new result, f of the new input. And then this has a mixing time of just one step. You just do one step, and you now have moved to a completely random u. And then if you look at what a quantum walk does in this case, then it just boils down to the same as Grover's algorithm. So quantum walks are a generalization of Grover's algorithm. But this generalization includes some cases that, again, we don't know how to do with Grover or with any non-quantum design techniques. For instance, distinctness. So this is finding unique collisions. This is an algorithm from Untitled from 2003. The situation here is we've got a function with 2 to the n inputs, and there's one collision in the function. Now, in the case of just basic Grover, we were looking for a root. In the case of Simon, there were many collisions where the difference was always this particular s. So any u and u plus s was a collision. But suppose now that f is almost injective, almost one-to-one, except that there's one input p and another input q, so that if you apply f to p and f to q, you get the same result, p different from q. Okay, can we find this collision? Well, normally you would think, yeah, you have to look at, I mean, suppose you try only half of the inputs, then you've got a 50% chance of getting P, 50% chance of getting Q, so 25% chance of getting both. And if you list F on all of those inputs, then you sort the results, or you can do this in more efficient ways. So you can figure out whether F has a collision on these half of the inputs. But already going down to half of the inputs has reduced the chance of finding the collision down to 1/4. And if you only look at 1% of the inputs, then your chance of finding the collision is 1 divided by 100 squared. So you're probably going to have to look very close to 2 to the n inputs to find the collision. Unbiased gets that down to 2 to the 2n over 3, 2/3 of n instead of n. Now, I'll have one slide here where I'll sketch how unbiased works to give you some flavor of what's going on and the kinds of things that are happening, which are, again, it's a generalization of Grover, the techniques being applied inside the quantum algorithm. And then, well, what does unbiased do with a quantum walk in order to solve this problem? Well, he replaces this function f by another function. This is going to be a slide with some Greek on it, so there's the function phi. Phi is applied to an input which is not one of the f inputs. It's going to be a set of f inputs, a set of inputs to the function f. And, well, how many of those inputs? It's going to be a set of size sigma. So unbiased chooses a number sigma, which is going to end up as that 2 to the 2n over 3, and says, let's consider this many inputs to the function f. And for one of those sets of inputs, let's call it s, let's define phi to give you two pieces of information. The first one, tau, is the number of elements f of I, where I is in the input set s. Now, that's usually sigma, but maybe you've got that f has a collision inside the input set s. Maybe p and q are both inside the set s. Excuse me, I'm going to drink a bit more water. And then assuming p and q are both in s, then tau is going to be, well, sigma minus 1, because there's one f of p and f of q, those are the same. So that compresses tau from sigma to sigma minus 1. And now this function phi is also giving another piece of information, which is the multi-set of all of the f of I values. Now, multi-set, that's not just the set. It's telling you how many times each f of I value is achieved. So in other words, it's listing all of the f of I values as a set of values, and also saying, if p and q were in there, that, hey, that f of p and f of q, that's achieved twice. So a multi-set is, instead of just saying, a set is saying for each element, yes, it appears, or no, it doesn't for all the elements outside the set. A multi-set is saying a set, but instead of appearing just once, it's appearing any number of times. In this case, it's appearing, well, once or maybe twice. So if S is including P and Q, the collision we're looking for, then tau drops by 1, and the multi-set says, hey, this f of P and f of Q, that f value appeared twice. And now unbiased defines goodness for the output of phi to mean that tau is sigma minus 1. In other words, the set S included the collision. And then the chance this happens is, well, like I was saying before, dropping quadratically with the size of sigma. So the chance of having S being good is sigma divided by 2 to the n, that's a chance of P being in there, and sigma divided by 2 to the n, that's a chance of Q being in there. Okay, maybe I'm being a little imprecise because there's like 2 elements P and Q which are guaranteed to be different, so I should have some. This is very close to reality. Sigma over 2 to the n squared is almost exactly the chance that P and Q are both in this set S. All right. To walk from one set S to another, Unbiased says the neighbors are the sets which have sigma minus 1 elements in common with S. So to move from S to a neighbor, you remove an element from S and you insert a new element into S, and that gives you a neighbor. And that's something where you can efficiently move from phi of S to phi of S prime, because when you remove something from S, you just compute the F value and then remove that from the multiset T. And then also while you're doing that, you can see whether the multiset said it was there twice, and that tells you whether tau is supposed to change. And similarly, when you insert, you can easily insert by doing one evaluation of F and then adjusting T and tau appropriately. It's just one evaluation of F, one change to the phi outputs, and then you're done. You don't have to run through all the other elements of S. Now, without a quantum computer, if you just did a non-quantum walk, then, well, you do sigma evaluations of whatever's in your initial set S to compute phi of S. And then to mix, well, clearly to be able to remove all your original elements and put in new elements, you clearly need something like sigma, well, at least sigma removal opportunities to move to any possible S prime. And the mixing time is something close to sigma. And then you also, in order to be able to find good elements, you need to repeat a certain number of times, which is the reciprocal of the sigma over 2 to the n squared. So you do 2 to the n over sigma squared outer loops. The quantum walk replaces the costs here. Well, the setup cost is the same. You still have to evaluate F sigma times. But the loops in doing the random walk are replaced by only square root of those loops. So instead of sigma, it's square root of sigma. And instead of 2 to the n over sigma squared, it's 2 to the n over sigma. And suddenly, this means that the optimal value of sigma is no longer close to 2 to the n. It is something like 2 to the 2n over 3, if you look at the formulas for a moment. Internally, inside quantum walks, what's happening is that it's a lot like Grover's algorithm of you take your input and then you negate if you're at the right result, if you're at a good result. But the diffusion inside Grover's algorithm gets generalized to some sort of diffusion along with your neighbors. Instead of diffusing all of the possible results, instead of flipping around the average of the entire vector, you look at the average of you and your neighbors and flip locally around the average of that. And that generalization, you have to work to exactly pin down what this means. There's definitely some cool stuff going on in Unbiased paper and then subsequent improvements of the quantum walk framework. But it's sort of spiritually, that's what's going on in this generalization of Grover's algorithm. And it really does more than what anybody knows how to do with Grover's algorithm. All right, I'll say a little bit about Shor variance. As we saw in Simon's algorithm, you have a vector of n bits, which you're exclusive oring. In other words, you're adding a vector of n bits modulo 2. Now, in Shor's algorithm, you replace that with addition of integers for factorization or addition of pairs of integers for doing discrete logs. Now, you can easily combine these and say, okay, I'm going to do addition in, well, the group Zn, so you have just the lattice of all possible vectors of n integers, and then you can mod that out by something if you want. It's sort of giving you more periods to work with, and you can find the extra periods that are beyond what you modded out by at the beginning. You can also, instead of having n integer variables, you could have n real variables. Now, there's always a question when you implement an algorithm on real numbers. What does that mean inside your computer? You have to specify, well, your real numbers are, for example, approximated by floating point numbers, like 0.58. Usually, instead of powers of 10, you use powers of 2. But in any case, you have to say, well, okay, the original real number computation is not exactly what I'm doing in the computer, and is it close enough that I'm actually getting the results I want? How many digits do I need to make it close enough? And is that a slowdown? Is that something which is making my algorithm go slower than it should? And well, okay, you can figure out how much precision you need for these algorithms. It starts depending on exactly what the input function looks like. And then something like being periodic, if you approximate that, well, you get something approximately periodic. And then you can generalize further to something which was approximately periodic in the first place. Have to be very careful. in defining these things, but you can generalize Shor to these groups, which are not just like a few integers or a few integers mod 2 or many integers mod 2. You can take many integers or even many real numbers. And then the result of these algorithms, again, I won't pin down exactly the hypotheses here, but the general flavor is to say you have a periodic function with some period S, some secret period S, which in general is going to be not just one choice of S. There are many periods of a function. Simon is kind of exceptional in that way, that Simon only has this one period S. For Shor's algorithm and then for generalizations, you generally have many choices of S. S and minus S and 2S, those are all periods. And any periods you can add to get more periods. Now, what the algorithms produce is some sort of random choice of period. What exactly does it mean if you have a random choice from a set that's often infinite? Well, you can pin that down. Maybe you have a Gaussian distribution, for example. Now, there's another direction of generalizing Shor's algorithm, which is saying all of these commutative groups on the previous slide, what if you replace them with a non-commutative group? You could have a function f, which instead of being f of, say, an integer is being added. Suppose you have f of, well, pick your favorite group, which is maybe much more complicated. Maybe you take, for example, the symmetric group Sn. So you've got some permutation of n elements. Maybe that's the input to f. And then suppose you have a period of that. So the periods of a function, that's the inputs that you can add in your group, or if it's called multiplication in the group, the inputs you can multiply to get the same function f. So there's this action of the group, whatever group you started with, on the set of functions, and then the stabilizer of the set of functions, if you want to sound fancy, that's another name for the set of periods of this function f. Typically in quantum algorithms, people don't talk about periods or stabilizers. They talk about the hidden subgroup problem. The function f is hiding a subgroup. The subgroup is the secret group of periods. And then this function f is something which, well, it is invariant under those periods. It has these periods. And then you're trying to find the group of periods. And finding random periods is basically the same as figuring out what the group of periods is. Now, this is a problem which has been completely solved in the following sense. You can, with a linear number of evaluations, quantum evaluations of this function f, I hope it's clear that the evaluation on the slide means quantum evaluations. This is generalizing Shor's algorithm and doing some more work. Linear number of evaluations of f, linear in the number of bits to specify your group, you can get enough information to pinpoint the hidden subgroup. Now, there's a little extra note here, which is the reason that people don't talk much about this generalization, which is that what does it mean to get from this extra information to the group? You don't have to look at f anymore. You do this constant times n number of evaluations of f. You have enough information, but then what is the group? There's this huge calculation you have to do, which is generally exponential time, to figure out what the group is, the hidden subgroup, the set of periods. So you haven't actually solved the same problem by this generalization of Shor's algorithm. And somehow what Shor ends up doing is something which, in the case of the commutative groups, immediately deals with this extra problem. But in the general case, you have to do, well, some exponential amount of extra work. Now, Kuperberg came along in 2003 and said, for certain groups, maybe for more, but well, he handled particular groups, the dihedral groups, and said for those groups, you can rebalance the extra work with a number of evaluations of f to get an interesting intermediate point. And what he says is that you can get the total number of f evaluations and the total amount of extra work you have to do, independent of f. You can get that down to, well, something exponential in square root of n. So in terms of n, that's more than a polynomial, super polynomial, but it is sub-exponential. It's below 2 to some constant times n. As n gets bigger and bigger, it's some intermediate range of complexity. But watch out for, sometimes people are sloppy and say sub-exponential where they mean super polynomial and sub-exponential. Sub-exponential means that you're going more slowly than 2 to the little o of n. That is sub-exponential. 2 to the something that converges to 0 times n. That is what sub-exponential means, which includes polynomial. If somebody says sub-exponential means super polynomial, no. That is not what the terminology means. Don't be sloppy about this. Super polynomial, sub-exponential runtime, that's somewhere between polynomial and exponential runtime. And that's how fast Kuperberg's algorithm is. Now, inside Kuperberg's algorithm, if you don't know what dihedral groups are, don't worry, I'll get rid of them in just a moment. inside dihedral groups, the hidden subgroup problem is something which is handled by Shor in the cases of certain hidden subgroups. There are certain periods which are easy to find by Shor's algorithm. And then Kuperberg's contribution is handling the other subgroups. And that boils down to something where you don't have to know what dihedral groups are, which is the hidden shift problem. So here you have two functions, f0 and f1, where f1 is the result of shifting f0. So f0, you apply this secret shift s to the input to f0, and you get this other function f1. You have the ability to compute f0 and f1, and then that's the function, well, the pair of functions that Kuperberg evaluates, something like 2 to the square root of n, well, there's some constant there, but 2 to the square root of n time, some constant in the exponent. So you have to be careful what that constant is. Some sub-exponential super polynomial amount of time to run Kuperberg's algorithm and figure out the secret shift s. Again, there's some restrictions on what happens if there's multiple possibilities for S, what do you get? But okay, this is the basic setup, and you can read the exact theorems for the conditions on these algorithms to work. Okay, if f0 were equal to f1, that would be a period of this one function. But when you have two different functions, that's the hidden shift problem. What do all of these algorithms do to cryptography? This will be what I finish off the entire talk with, and then let people go. So first of all, if you run your browser today, I fired up Firefox, or you can take Chrome or whatever browser you like. You can say, go to google.com or your other favorite website and say, what is the encryption being used? For Firefox, it's easy to click on the lock and click on more information, and it shows you the algorithms being used. You can click on the certificate, find out the signature algorithms. For Chrome, I actually haven't figured out how to get all this information. Some of it you can see, like the certificate, but I haven't figured out how to get the rest. And there's other browsers maybe that make this easier. You can also monitor the network and figure out what the algorithms are. Anyway, Firefox to Google a few days ago was using the following. First of all, the encryption is using AES 128. And that's what's encrypting all your data. There's all the data back and forth to Google is encrypted using AES 128 with some 128-bit secret key. It's also authenticated so that the attacker can't change anything. And GCM, that's, well, using AES 128 in an authenticated encryption mode, which is protecting your data against modification. The key for AES-128 GCM is something which is exchanged using Diffie-Hellman, elliptic curve Diffie-Hellman, using the elliptic curve 25519. And then the Diffie-Hellman key exchange there is a completely unauthenticated Diffie-Hellman, except that fortunately there's a signature saying, yes, this is from the server. And that signature is, well, the google.com key is a certain key signing the key exchange. So you know that, yes, you are talking to Google. And that key is it's another elliptic curve key, this time a signature key using ECDSA. And the elliptic curve used there is the NIST P256 elliptic curve. And then that key is certified by a higher level signing key. So the certification is saying, yes, this is Google's key, and that's signed by a certain authority. And that authority has an RSA 2048 key to sign that information. And that authority is something that, well, has its own key certified, so signed along with something saying, yes, this is a legitimate authority. That is signed by a certain root of trust, an ultimate key which Firefox knows is something it's supposed to trust. It's just programmed into Firefox, trust that final RSA 4096 key, which signs the RSA 2048 key, which signs the ECDSA NIST P256 key, which signs the key exchange, which by X25519 gives you the AES 128 key, which encrypts and via GCM authenticates your data. Also, this is not the complete laundry list of algorithms because there's also some hashing. If you look around, you see some SHA-256 and some SHA-384. Okay, so that is current Firefox Google cryptography. What happens when you pull out an attacker with a quantum computer? Well, Shor's algorithm is taking 4 of the layers here and breaking all 4 of those layers. If any layer breaks, then the whole system's insecure. But well, four of these layers there's 2 RSA keys, and then there's 2 elliptic curve systems, and all 4 of those are broken by Shor's algorithm in polynomial time. So panic! Well, okay, if you listen to people saying that you should panic just because there's an algorithm that breaks something, then, well, maybe you don't have to worry so much. Because, for example, nobody has a quantum computer. This is a common response to panicking about Shor's algorithm, which says that, well, okay, let's wait until we see whether people can actually build a quantum computer that's big enough to run this algorithm. IBM's 127 qubits, those are noisy qubits, and it's not enough qubits anyway. And we'll see later how many qubits you would actually need, noisy qubits you would actually need. IBM says it's going to get to 400 next year and 1,000 the year after that, but they will have to go much farther to run Shor's algorithm. We'll quantify that in a few minutes. The thing is, even if IBM and Google and so on don't have a quantum computer now or even in 5 years, we still have a problem. The first part of the problem is that attackers have their own quantum computer manufacturing programs and projects, and they're not telling us how far ahead they are of the public. They're certainly not behind the public. I mean, they can do everything that Google can do, and they can read Google's papers, and they invest huge amounts of money in doing their own computer engineering. But they could be years ahead. I don't know. I mean, it seems like quantum computers are really hard to build, and surely they can't be 5 years ahead or 10 years ahead, or, well, who knows? Once the attackers do have a big enough quantum computer, which is certainly no later than when, like, Silicon Valley has a big quantum computer, the attackers are not going to say, yes, we have it. And if that is years ahead of when Silicon Valley has it, then we don't know. So if we're just basing our decision making on IBM hasn't announced one yet or Google hasn't announced one yet, then, well, we're not actually looking at the problem, which is the large-scale attackers who are going to be attacking us with these quantum computers. Google and IBM hopefully won't be attacking us with these quantum computers. But large-scale attackers, once they have quantum computers, which could well be years earlier, they will be attacking us. Now, next issue is that any sensible attacker right now already, well, for years, would have been recording all of the ciphertexts that you're sending and storing those, saying that, well, once we have a quantum computer, we'll start decrypting those ciphertexts. And maybe some of the secrets there will still be interesting years from now. This is not just, of course, a common sense attacker is going to do this, but there's actually leaks from some attackers which are saying that, yes, they are in fact doing this. So this is, it's not just being paranoid. This is, I mean, it's common sense, and there's evidence that attackers are in fact doing this. So there's lots of ciphertexts that are the ciphertexts we're sending today, encrypted with, for example, elliptic curve cryptography. And those things are, well, recorded. I mean, copies of those are recorded in big databases, and then the attackers are going to prioritize some of those that they find most interesting and decrypt those once they have a quantum computer. So we already have a problem today that our data will be exposed, which, depending on the number of years that you care about your data, this could already be a problem today. Also, if we're going to upgrade to cryptography, the whole point of evaluating security and saying RSA and elliptic curve cryptography are not good enough, the point is to say, okay, let's switch to something else which is secure. And then this upgrade is something which, well, it's some companies can do this quickly, but most companies and most organizations running network services and other kinds of uses of cryptography, they are not going to instantly be able to switch. And they need, I mean, there need to be standards, but also a ton of real world engineering work and deployment to be able to actually move everything over to some new cryptographic systems. So we do have a problem today in figuring out like what we're going to do to protect ciphertext being sent now, which is not something that we can instantly deal with. I mean, security problems that we're facing now is not something you can instantly fix. And also, looking ahead a few years, we're having bigger and bigger problems because quantum computers are coming closer and closer, and we won't even know when they have actually arrived and attackers are using them. We're going to get some maybe years later announcement from, say, Google. Okay, so panic. You might still say, well, okay, this polynomial time, is that really a problem? I mean, there's lots of polynomial time algorithms where they're quadratic time or even faster, and you try them on big examples, and yeah, they do run really fast. But there's also some polynomial time algorithms which have really big exponents in the polynomial or really big constant factors, and that makes them really, really slow. And actually, maybe it's not a threat. Well, this is something that's been analyzed. There's this paper by Gibney and Ekero, which I've linked from the slides. Has a great title. It says, How to Factor 2048-bit RSA Integers in 8 Hours Using 20 Million Noisy Qubits. I like titles like this, which actually communicate something. I don't like titles which are like clickbait, like one weird trick to improve your quantum cryptanalysis. Now, this is a title that actually says something. 8 hours, 20 million noisy qubits, which are like IBM and Google's qubits. If you have 20 million of those instead of 127, then you can factor a 2048-bit number in 8 hours. There's some assumptions here. They make plausible physical assumptions for large-scale superconducting qubit platforms. They're also doing a lot of work to get this result. They're improving how Shor's algorithm works. If you look at the details, then, well, the assumptions are plausible. I mean, we don't have 20 million noisy qubits, but what they're saying about what a superconducting qubit computer would look like in order to do big computations, numerically what they're saying, it sounds like, yeah, this is plausible engineering. We're not there yet, but it's not unreasonable. The main difficulty they're facing, where most of the work is going, is saying, well, these noisy qubits are not the same as the perfect qubits that we were using to design algorithms. Shor was saying, yeah, you've got perfect qubits, but then already Shor was very early doing error correction and saying, yeah, actually the qubits we make are not going to be doing these perfect operations. So what happens if they're slightly off in the gates they compute? Errors are going to build up, and then you don't get to apply your normal error correction. Like in normal computers, there's these your zeros and ones are sort of locked into place. That's a lot of what makes transistors really work, is that they're kind of locking zero into zero and locking one into one. They're doing error correction with every operation. Now, inside quantum algorithms, it's not that easy. You have to do a lot of extra work to do error correction. And this is something where, well, you have to, instead of the logical version of Shor's algorithm using perfect qubits, logical qubits, where you say, oh, I only need something like a few thousand qubits for Shor's algorithm. If you do error correction, that goes up to millions, well, 20 million noisy qubits to run Shor's algorithm. Okay, it's a lot of qubits. IBM's not there yet, Google's not there yet, but it does seem feasible. It's something where you can imagine in 10 years, less than 10 years even, it's totally possible that people are going to have this publicly, and then could be years earlier that the attacker's putting many millions into breaking these things, that they're going to have quantum computers earlier, and 8 hours, it's not that much time, and then, okay, so a bunch of 2048-bit RSA keys get broken. The same paper is also looking at discrete logs, not elliptic curve discrete logs, but traditional discrete logs, like you have multiplication, like I was saying before, with 4 to the u times 9 to the v modulo big prime p, saying suppose you use 2048-bit DSA, for example. And then in that situation, it's slightly faster, 7 hours, and slightly more qubits, 26 million qubits. And you can also follow links to some more papers which are looking at elliptic curve discrete logs, which are more complicated operations inside F, but the sizes are typically smaller, like 256 bits, so that makes things, the costs are overall somewhat lower. These numbers for how long it takes inside Shor's algorithm to do, well, it boils down to a quantum modular exponentiation inside Shor's algorithm, or quantum double modular exponentiation inside the discrete log version. You can compare those to the costs of doing non-quantum modular exponentiation. And the reason to do this is this gives you some idea of how expensive qubit operations are compared to bit operations. The final numbers say that, well, an Intel CPU doing non-quantum modular exponentiation is millions of times faster than 8 hours or 7 hours. And if you think about, well, how expensive is it to do the engineering of a quantum computer, maybe the costs will go down, but at the moment it looks like it's going to be millions of times more expensive than an Intel CPU core. So overall, a qubit operation, doing a quantum bit operation inside this modular exponentiation, which is most of the work inside Shor's algorithm, that's looking something like 2 to the 40 times more expensive. I mean, you spent 2 to the 20 times as long, and you're also spending 2 to the 20 times as much money. So for the same time and same investment, you could have done 2 to the 40 times as many operations. So this suggests that a qubit operation is about 2 to the 40, maybe even more bit operations in the effective cost. Still feasible to do Shor's algorithm, even with this big cost of each qubit operation. Now, this 2 to the 40 is not something you should take as, oh yeah, it's definitely 2 to the 40, because maybe the cost of qubits after some work on engineering these computers and doing mass market quantum computing, maybe it actually gets a lot cheaper. And maybe it's only 2 to the 10 times as expensive to do a qubit operation compared to a bit operation. And then the speed of it, well, that's something which depends a lot on this error correction. And maybe qubits get engineered to be less noisy, and then you can get away with less error correction. Maybe the qubits are, the normal way you design a chip is you've got everything connected by wires which have to go, like, I mean, each wire is consisting of short segments. And I mean, you can think of a wire as a long wire transmitting data from here to there, but it's really built from, you've got, a lot of silicon going from here to there. And then, is it silicon or copper? I don't actually know anything about the physical design of computers. I know there's some silicon involved, but anyway, I think that's, there's definitely some silicon involved in laying things down on the chip. And then, the good thing about designing algorithms is you can get away with abstractions. Again, you don't have to think like, what are voltages actually doing, and what does the periodic table say these elements are, and why do transistors work? You can just say they are doing the following abstract computations. So anyway, you've got inside a chip, I'm sure about the fact that a chip is a two-dimensional thing. People might have a few layers, like 8 layers or 16 layers, but it's really like 10,000 transistors by 10,000 transistors connected by these wires, which are, well, really just moving locally from one side of the chip to another side of the chip. And then if you say, well, actually, there's some way to do, for instance, quantum teleportation, or some other way to not just have like you're moving data to your near neighbors in a bunch of steps to get across the chip, then you would be able to do some faster quantum computations. That would save a lot of cost in these algorithms. It might be that even if the noisy qubits are as noisy as currently predicted, as people are currently trying to build, and they don't get much better, it might be that there's better ways to do error correction. Like, this is something that has improved quite a bit over the past 20 years, and people have new ideas for algorithms to do error correction, like build logical perfect qubits on top of noisy qubits. And that's something which could save a lot of cost. And also reversibility. This is something where, again, all of the operations, like Toffoli, is not just making a new AND of something, it's XORing it with something else. And that having to be always like doing these reversible basic operations changes how the low levels of your algorithm design work. And that's something where people are learning more techniques to do that efficiently, to streamline the algorithms, which is somewhat different from non-quantum algorithm optimization. There's also reasons that if you look beyond Shor's algorithm, then you really have to rethink what the cost of your algorithm is. Like modular exponentiation, main bottleneck in Shor's algorithm. There's papers optimizing that for regular chips, and there's papers optimizing that now for quantum chips. But what if you look at some different algorithm? Well, you can't assume that the cost ratio is going to be the same. For instance, if your algorithm is using a lot of XORs, then those are much, much cheaper than ANDs, which is different from the normal chip situation, is that NAND is very, very cheap, XOR is somewhat more expensive. In a quantum computer, doing Toffoli is like 2 orders of magnitude more expensive than doing an XOR, a C0. Also, when your algorithm is easier to reverse, which is something Shor is maybe one of the easier cases there. The way that Shor is typically done is very smooth reversibility. There's some algorithms which are harder to reverse, and there's a lot of techniques and investigation of that. Also, the error correction is not just, well, you paid this overhead for error correction. It's something that depends on how big your computation is. Generally, bigger, longer computations need somewhat more cost for the error correction compared to the cost of using just logical perfect qubits. There's more of these issues. So you really have to analyze what the costs are of your algorithms. Don't just assume it's like take the cost on an Intel chip, multiply by 2 to the 40, that's your quantum cost. It's more subtle than that, in part because of technology and in part because of algorithm optimization. Okay, what about Grover's algorithm? Well, inside AES, there's this 128-bit key if you're using AES 128, and that means there's 2 to the 128 possibilities, and you could just say, okay, I try guessing a bunch of possibilities for that key. And then for each guess, what do? Well, you take the ciphertext, you try decrypting using that key, and decrypt the first block, the first 16 bytes of ciphertext, and then you get, well, if it's from Google, it's probably going to start HTML, head, meta, blah, blah, blah. And you can just check, do I get exactly that pattern? Okay, maybe Google changes it to something else. But in general, if you're trying decrypting ciphertext, you can, from a very small number of blocks, very small number of AES computations, you can recognize, have you in fact found the correct key? And if you didn't find the correct key, then you try some other keys. Try a bunch of keys in parallel and keep repeating until you find the correct key. Now, this is something which on average is going to take you about 2 to the 127 guesses of the key, which is, it's something which, I mean, that's a big number, 2 to the 127. Here's a baseline for comparison. People will sometimes say, ooh, Bitcoin is using a lot of computation. That is 2 to the 92 hashes per year currently. It's not like the entire world's power supply, but it's using some power for that, and it's a lot of computers involved, a lot of special purpose hardware, which is designed to do hashes as efficiently as possible. And well, okay, maybe the serious attackers have slightly better chips, but getting from 2 to the 92 to 2 to the 127, we would probably notice the power consumption for the like computer center, which is doing anything like 2 to the 127 guesses. So, okay, we tend not to worry about people doing approximately 2 to the 128 computations. Grover is, as I said before, 2 to the 64 quantum evaluations. The thing is that this gets multiplied by the 2 to the 40 that I mentioned before. Or if you count bit operations, the one AES computation is something like 2 to the 15 bit or qubit operations to evaluate. And that means if it's about 2 to the 40, you have to, again, evaluate. There's lots of question marks about the 2 to the 40, but roughly 2 to the 15 qubit operations is about the same cost as 2 to the 55 bit operations. Multiplied by 2 to the 64, that means the attack is about 2 to the 119 bit operations. Or another way to think about that is that's about 1,000 times current Bitcoin bit operations per year. 1,000 years of current Bitcoin, or well, again, you can imagine a larger scale attack than Bitcoin, but this is still, it's a pretty big number of bit operations. Originally, AES 128, if you just do a straightforward attack without quantum computers, it's more like 2 to the 143, maybe a little better bit operations. So this is significantly fewer bit operations, but still pretty expensive. So a lot of people will look at this and say, yeah, that's a lot. It's maybe better than the 2 to the 143. It's some speed up, but I mean, when you take that qubit to bit cost ratio into account of something like 2 to the 40, it means you're a lot less worried about the 2 to the 64 improvement from Grover. Now, there's another reason that people often point to as being even less reason to worry about Grover, which is that the speed of Grover's algorithm, it's really important to pile up those repeated negation operations inside Grover's algorithm. And you have to do those serially, otherwise you don't get that pile up. So you have to do step 1 and step 2, and then step 1 and then step 2, and then step 1 and step 2. Those iterations serially, sequentially, that's what's giving the speed up in Grover's algorithm. But if you serially did 2 to the 64 nanoseconds, just imagine an iteration being doable in a nanosecond, which sounds a little hard to believe, but suppose you could do that. 2 to the 64 nanoseconds is 500 something years. That's a pretty long time. Maybe the attacker is going to run a 585-year computation, but it's a little beyond what we tend to think about in cryptography. Now, the attacker could say, okay, I'm just going to run Grover for only 0.5 years. So 2 to the 10 times faster. But then the success chance goes down quadratically to 1 over 2 to the 20. So the attacker has to run 2 to the 20 quantum computers in parallel, guessing different parts of the key space. The overall cost goes up by a factor of 2 to the 10 to about 2 to the 129 bit operations, which is still less than what AES is currently doing. But if the iterations are actually slower than this, and the attacker needs to go 2 to the 20 times faster, then the overall cost goes up to, well, basically very little speed up compared to, if anything, compared to the current cost of a non-quantum attack against AES. All right. Is it faster than an AES attack? Well, yeah, maybe. I mean, this really depends on exactly that 2 to the 40 cost overhead and how long the attacker is really willing to wait and exactly how fast the iterations can go. It's maybe faster than a normal non-quantum AES attack, for risk management, you should imagine quantum computers being good enough that this could be faster than a non-quantum attack, but it's clearly not as expensive as a Shor attack. It's not as scary as Shor's attack running in, 8 hours against RSA 2048 using 20 million noisy qubits. The end result of this, lots of people will say, yeah, okay, we can keep using AES 128. Now, I disagree with that for reasons having nothing to do with quantum computers, actually, which is that lots and lots of times, AES 128 is not just you have to look at one ciphertext and guess one key, but there are many, many protocols where you can apply multi-target attacks, where you have, for instance, lots of keys were used to encrypt the same standard plaintext in a way that allows the attacker to just look at all of the ciphertext and guess one key and very efficiently compare like neutral decryption without having to do the work on every separate ciphertext doing the work. It's like you can do a trial encryption of a plaintext and then look that up quickly in a database. Well, okay, it's maybe a big database work, but there's all sorts of tricks to make that go much, much faster and basically reduce the communication costs, the database lookup costs. And then you get some very, very fast multi-target attacks where if you have, say, 2 to the 40 targets, say millions of users each sending millions of ciphertexts, sometimes the 2 to the 128 guesses goes down to 2 to the 88 guesses. And that is feasible today. That's less than what Bitcoin is doing in a year. So just switch to AES 256. It's only a little bit more expensive than AES 128. And there's very few people who have trouble with the cost of AES 256. Or even better is use Cha-Cha, which has a bigger security margin. It's on Intel chips, depending which Intel chip, it might be a little faster, might be a little slower, but again, the cost doesn't matter. So just use Cha-Cha. Again, the security margin is more than AES 256. Plus, on platforms that don't have AES hardware, AES is much slower and tends to be implemented with timing attacks, and Cha-Cha avoids the block size attacks that break a lot of protocols using AES, whether it's 128 or 256. Okay, enough advertising. Let me get back to the quantum cryptanalysis situation. Whenever you're using Grover's algorithm for quantum search, you always have to look at these questions of, okay, how many years is the attacker going to say, I'm going to have the results being coming out, say, 585 years from now? No, that's too long. How about 1 year? How fast can I compute my function f? And then how many iterations of f can I do sequentially in, say, 1 year? And then is that more than the 2 to the 40? Well, it depends on what exactly the 2 to the 40 actually is for the cost ratio for quantum operations. But this is something where, depending on the answers to these questions, Grover search really might not be useful. If you assume that quantum computers work pretty smoothly, then you can imagine, again, that Grover does make some searches faster, but you really have to look at how much this function f that you're searching for costs. And if it's an expensive function, then you're going to get that, no, Grover really doesn't help. And that's the situation for lots of Grover applications in the literature. There's lots and lots of Grover applications and quantum walks where people need to use a ton of memory, for example, in evaluating f. I've got one example on the slide, which is suppose you're trying to find collisions in SHA-256, which breaks some protocols. You can design protocols so they're not broken by collisions. But suppose that you're saying, I'll use SHA-256 and I care about the collision resistance. Well, there's a standard way to do 2 to the 128 SHA-256 evaluations with very little memory, which will find a SHA-256 collision. If you pull out your quantum computer, there's a quantum algorithm which will reduce the 2 to the 128 down to, well, 2/3 of the exponent, 2 to the 85. You could do that with unbiased. There's a simpler way to do that using Grover's algorithm. And then these algorithms, whichever way you do that, these quantum algorithms that do 2 to the 85 SHA-256 evaluations, wow, sounds much faster than 2 to the 128. Sounds faster, sounds like a few weeks of Bitcoin. This is something where you can imagine the attacker doing that if you ignore the 2 to the 40 overhead. But what you cannot ignore is, I mean, even if you say, oh, the 2 to the 40 is somehow going to get much better, you really cannot ignore the fact that in this attack, you were doing 2 to the 85 lookups in a database of size 2 to the 85. And that makes F much, 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 much more expensive. And that means that Grover search really cannot work. Even if you say quantum computers are really fast, even if you scale up to bigger than 128 and say, is there an improvement? There really is no improvement from this algorithm because of all of the overhead of doing memory lookups. There's no physical realization of a quantum computer anywhere in the literature as something that you could imagine building, something where people say, okay, look, if you lay out atoms like this, then you will have this quantum algorithm actually saving time in collisions. So collisions are an example of something where you really should learn the non-quantum algorithms for that, because we don't have quantum algorithms that do better at all, even if we're super optimistic about how quantum computers are going to work. You have to imagine that somehow those memory lookups, the database lookups, are going to go away in order to find this algorithm interesting. All right. Last little section of my talk here is on post-quantum cryptography, which is saying, what does cryptography do because of, well, Shor's algorithm? That's really the motivation here. I mean, Grover, yeah, okay. You could just say move up to 256 keys, and it certainly deals with Grover, and maybe Grover's algorithm doesn't actually work at all. But Shor's algorithm is really, really scary. So what is happening in response to this? Well, there have been a bunch of conferences, PQ Crypto conferences. They've accelerated to being every year now and getting to a huge number of people attending. Of course, as we've seen now, maybe physical attendance at conferences is not so easy, but the conferences are continuing one way or another. After about 10 years of serious public attention to post-quantum cryptography, finally NSA issued a statement saying, yeah, we expect there will be a transition to post-quantum cryptography in the future. And then 8 days later, they issued a revised version of the statement saying, NSA will initiate a transition to post-quantum cryptography. Yeah, that was not very impressive. Then NSA's friends at the US National Institute of Standards and Technology started a project to standardize post-quantum cryptography, which received 69 complete submissions of systems, signature systems or encryption systems. Almost all of those have lost security. Not completely lost security. About half of them are less secure than the claimed security levels. The other half, the sort of survivors, those have lost security, but they had enough of a security margin that their security claims haven't been broken. So out of 69 submissions, there's about 30 which are is still not shown to be broken by any attacks that are known after a few years, while the other 30-something are shown to not meet the original security claims. And the security picture, there's a ton to say about attacks, even ignoring quantum computers. There's tons and tons of new attacks this year. And, well, this is terrifying. This is something where if you look at, for instance, the AES competition or the SHA-3 competition, then the final candidates did not lose any security. It's really, there are no attacks that are better than, like against SHA-3, there's just nothing that does better than just the obvious attacks against SHA-3. There are reduced round attacks. You can say, here's a simplified, smaller version of SHA-3, which you can break, but there's really, the full SHA-3 has not lost security. And that's something where, if you look at the finalists in the NIST post-quantum competition, then they definitely have lost security. There was just a paper a few days ago, which was at AsiaCrypt, which was saying, yeah, so there's a loss of something like 5, 10, 15 bits of security for Kyber, which is a candidate that has attracted a lot of attention. And it's just because, well, there's another attack, a better attack than what they had thought of. And cryptanalysts are really struggling to deal with all of these different post-quantum systems. It's a much more complicated attack picture with many more attack avenues than what we have in symmetric cryptography. There are many interesting attack ideas which can get through some number of rounds, but just really do not break the full systems. Whereas for these post-quantum systems, they really are losing security. There's attacks which are doing better at breaking the proposed systems, and that's terrifying. There's surely going to be more attacks, which we don't know today. I mean, there'll be more attacks in 2022, 2023, and, well, hopefully whatever gets standardized is going to be secure, but I'm scared. Okay, last few slides is what is happening for quantum cryptanalysis of these post-quantum systems. Well, I've got a few little categorization here, a few ideas of how to think about what's going on. So sometimes people say, all right, let's look around at interesting cryptographic attack algorithms and say, hey, inside this attack algorithm, there's a search. And sometimes it's not stated that way. You have to reformulate the algorithm to find it. But often there's a big search, which is saying, I'm just looking through a bunch of inputs and saying which inputs are good inputs. And then you can plug in Grover. And that's something which has produced state-of-the-art attacks against not just AES, if you assume that Grover is fast enough to make a difference, which again, maybe for AS128, it's something which is faster than normal non-quantum attacks. But okay, under the same assumptions that Grover could maybe save some time, you get similar speedups for, say, pre-images in hash functions attacking signature system like Sphinx Plus, hash-based crypto. You have the fastest quantum attacks, again, under the same assumptions, quantum information set decoding against a code-based system, classic McLeese. You have the fastest multivariate quadratic attacks, generic attacks, quantum XL, against multivariate quadratic systems. And all these are using Grover. And then for lattice systems, there's one type of attacks, enumeration, where quantum enumeration is this kind of attack. It's maybe a little tricky how the combinatorial search is working in there, and it helps to do something a little beyond Grover to make that work. But it's basically just another Grover application of recognizing something as a big search. Now, there's some, what I'm labeling as big Grover applications, and this is where the big search there is doing something much more expensive inside the inner loop, like using a lot of memory or doing some collision searches where without quantum computers, there's some clever ways to get rid of the memory usage, the communication inside collision searches. But for the quantum speedups that we know, you really have to imagine, even for gigantic sizes of these algorithms that can overcome the 2 to the 40 qubit cost, you really have to imagine some science fiction improvement beyond what we imagine for quantum computers in the next 10, 20 years, which is making the memory costs go away in order for quantum algorithms to speed these things up. Now, people investigate these hoping there's going to be some magical way for memory costs to disappear. And so that's where we get the quantum collision attacks I mentioned before, or very similar to that is the best quantum attack, assuming memory costs disappear, against Psych, which is isogeny-based crypto. Quantum sieving, that's another kind of attack against lattice systems. There's 2 recent papers which are improving that using quantum walks. And then there's also quantum combinatorial attacks against lattice systems. All right, another category is Kuperburg. Now, this is something which is attracting a lot of attention because 10 years ago it was used to attack CRS. So this is an isogeny-based system, which is different from Psych. CRS is smaller than Psych and provides non-interactive key exchange. But the Kuperburg application to CRS said, well, it's only providing sub-exponential cost, sub-exponential security, super polynomial. Still, you can scale up to get past that, but it's maybe not as secure as you want. Maybe in the interest of time, I'll skip past my parenthetical comment about Psych. It's interesting that there's a lot of interest right now in these 2 different directions of isogeny-based cryptography, one of them represented by CRS, or the modern version of that is Seaside, and then one of them represented by Psych. Okay, Shor applications. This is something where what I find by far the most interesting about this, beyond the RSA and discrete log application, is that there's certain kinds of groups related to algebraic number fields, unit groups, class groups, and so on. And in these groups, you can use Shor, a continuous version of Shor, to compute discrete logs. And that, along with some more number theoretic algorithmic ideas, broke Gentry's original fully homomorphic encryption system from SOC 2009 in the case of cyclotomics with some technical condition, H plus equals 1, which is the normal case. This is like people are usually using cyclotomic number fields with H plus equals 1. And this is a polynomial time attack, breaking a major crypto system, also the first multilinear mapped system. This is something where it's really worrisome that there's these attacks against major crypto systems appearing just a few years ago. And then I've got a link to some very recent work on S-unit attacks against ideal SVP. I would recommend not relying on ideal SVP for any cryptographic systems. Last slide, a few more categories here. Maybe beyond Grover and beyond Shor, and I mean beyond quantum walks and variations of Shor like continuous HSP, maybe there's some better quantum attacks. I've got a link here to a paper which is saying it's doing some lattice attacks which are not known to be doable without a quantum computer, and it's doing some slightly different quantum algorithm. It's not the same as the algorithms that I've mentioned so far, which is attacking these problems in polynomial time. Almost the last category here is cost analysis. This is something I love doing, is saying, okay, you've got an algorithm, it's about 2 to the n or 2 to the n over 2 or n squared, but okay, really, how much does that cost? And that's what leads to, for instance, the things like 8 hours and 20 million qubits. And there's lots and lots of these algorithms where it's really fun to analyze exactly how expensive these algorithms are. On the slide, I've got 4 links in much more detail to 4 examples of recent work on this. And last category, if you run out of other ideas for breaking things with quantum algorithms, then just try changing the crypto systems. Now, you can justify this by saying, well, maybe the user is going to do this. For instance, one thing you can do is say, maybe the user is going to take their secret key the actual legitimate user is going to have the secret key. Maybe they'll use that on a quantum computer and apply that to decrypt some ciphertext from the attacker, which is not just decrypting like a normal ciphertext as bits, but maybe the attacker can use a quantum network to send some qubits, which could be all of this long vector, and the decryption happens everywhere in the vector, and maybe the result of that decryption goes back to the attacker, and maybe, well, that does allow some attacks which are not allowed by the original non-quantum crypto system. And it's analyzing what you can do in this situation. It's certainly intellectually interesting. I don't imagine that in the near future I'm going to be using any quantum computers for my own secret keys. But if you imagine far in the future that somebody might be doing this, then these crypto systems could definitely be of interest. That's it for quantum cryptanalysis. Thank you for your attention.
So thanks, Professor Bernstein, for such a nice talk. It's really interesting and we are really grateful to have you here. Now the session is open for the questions and the discussion from the audience.
Are there questions in the chat box? Just check. I see some 4 comments in the chat box. Can you just check the chat box?
I also see a red thing, but maybe.
No, not yet. Any question have come in the chat box.
Okay. So I have one question, Dan.
Yeah.
So are you discouraging the manufacture of quantum computers?
You mean discouraging for like ethical reasons that quantum computers are?
No, ethical or unethical, both way.
It's quantum computers are scary, and I think when people are building quantum computers and saying, well, technologically we can do it, so let's do it and it'll be fun and maybe it's useful. Of course, people, when they're doing these things, they will say what the possible positive applications are. For example, fertilizer. This is something I've lost count of the number of times I've heard this from people who are doing quantum algorithms. They will talk about fertilizer. So what they say is that something like 2% of the world's energy consumption is devoted to fertilizer. And a quantum computer could do quantum chemistry calculations, which would maybe, actually, I think it's plausible that would give us better fertilizer. There's been lots of research into chemicals used in fertilizer, and that has improved the energy consumption of fertilizer. And with better quantum, better simulations of the quantum effects of different chemicals, you could build better fertilizer, which would reduce a noticeable part of the world's energy consumption. And I mean, that's just one example of an application. It sounds positive, and there's many other possible applications. One time I was logging into a supercomputer and looking around at what programs people were running, and this was a shared supercomputer with lots of people. And one of those programs was called NAMD, and this was something about molecular dynamics. And there's another one about QCD, quantum chromodynamics. And these are things that a quantum computer would be able to do accurate simulations of these more efficiently if there's a big quantum computer. It seems plausible that these would be able to do physics simulations, which are useful for whichever applications people are running right now. And so this is something where there are possible applications of quantum computers which are useful. of course, the people who are actually doing research into building quantum computers and making the engineering work, they're doing it because they love doing it. And then the fact that people are willing to pay them for doing it, well, it's nice and it's great and hopefully it's useful, but this whole process of thinking there's these positive applications that might work and it's a fun thing to be working on. Nowhere in this process do people ever have to think, what is the damage done by what I'm doing? And this is a story which is told again and again in science of you have people who are having fun doing their science and producing maybe useful and sometimes actually useful results, and at the same time having some serious negative effects, which, I mean, look at the damage that Facebook does to the fabric of society. It's something where, okay, maybe you can fix these problems, but it's something where when people are developing Facebook, they don't start by thinking, well, here's the damage that we're going to be causing. Now, attackers have a great time with this. If there's something which is useful for attacks, then somehow attackers don't have to be worried about the ethics of things because, well, they're attackers. I mean, that's their whole goal is to attack things, break things. And, well, if they have a big quantum computer which is doing lots of damage to the integrity and confidentiality of information, then that's their job. People who are building quantum computers and maybe helping the attackers, I would not recommend that we try to stop attackers by stopping the development of quantum computers, because I don't believe it's effective. I don't believe that if we turned off the public analysis and the public development of quantum computers, if we said, the damage is too big, we have to turn this off, I don't think that would stop the attackers from actually building these quantum computers. There was, for example, one of the attackers, some leaked documents in 2013, said they already had a budget of $80 million US per year, maybe that says something about who the attacker is, for building quantum computers. And the budget has certainly gone up since then. And this is a huge budget. Now, this is something where we have no idea what various other countries are doing. And I don't think that by turning off the public development, we're actually going to make a difference, maybe a tiny difference. There are clever people working publicly, and they're going to have ideas which maybe the attackers missed. But I would not underestimate how much work is going on in secret to build quantum computers. So I don't think that by saying, oh, let's stop the public development, that will save us from quantum computers. I don't think that's going to work. I think we have to consider what the attackers are doing secretly. And in some sense, developing quantum computers publicly and having somebody factor a 2048-bit RSA key, a challenge publicly, that will be great motivation for people to make sure, if they haven't already switch to post-quantum cryptography, and then they'll have a chance of protecting themselves. So you can think of public development of quantum computers as an advertising mechanism for, yes, quantum computers do work. Maybe they don't work. Maybe something will go horribly wrong. There are a few people who say, oh, quantum computers, actually, they'll fail. And then, okay, we don't have to worry about them in that case, except, well, for risk management, it looks like they could work. I mean, best guess now is they will, and that's really scary. And so we have to protect ourselves somehow. And then the best thing we can do to figure out what the scope of the problem is analyze the capabilities of the computers that the attackers are presumably going to have built.
Okay, thank you. I got it. Thank you very much. Oh, super talk.
Thanks.
So
are there any other questions? Formally thank and close the session. Follow me.
Yes. So thank you so much, Professor Bernstein, for the session, today's session. Thank you for time. And it's really a nice talk, and we have enjoyed it a lot, and we have learned a lot, moreover. And I also want to thank the session chairs, Professor Bimal Roy and Professor Ravi Garki, for their time and for their guidance also. So today we will call it a day now. And the next session tomorrow, we have an inauguration session for the conference itself, Indocrypt 2021. And that will be starting at 11 o'clock. And before that, we'll be having the registration for the participants at 9 a.m. Okay, so thank you.
Thank you. So I thought I heard another question.
Yeah. There is a question. So, in the ambiguous algorithm, like we are finding the collision, right? So, what if there is more than one collision? How does the complexity changes? Like similar to finding similar to Grover's algorithm case where if there are more than more than one element of good elements, right?
Mm-hmm. Yeah. So the question was, if I understood correctly, is like you have more collisions in Unbiased algorithm by analogy to Grover's algorithm having more roots. What does that do to the complexity?
Yeah.
And yeah, it's one way to think about it is suppose you have a function with many collisions. Now you have to be a little bit careful because there's two different ways that a function can have multiple types of collisions. One way is it could have many inputs that pile up on the same output. You have a multi-collision. Now, a different way is you could have like these two inputs collide, these two inputs collide, these two inputs collide, etc. The analysis is a little different between those cases. Maybe the simpler case is when you have like these two inputs collide, these two inputs collide, and so on. And in that case, if you do a random restriction of the function, then if you think how much do you restrict the function in order to get one unique collision, then that will, and then apply unbiased. That will be reasonable results where I haven't seen something better. Maybe somebody has an idea for doing a better algorithm in that case. The multi-collision case where you have like many inputs with the same result, in that case, it seems like slightly different techniques are required for the best results. This is something where I've seen a few papers, but I haven't absorbed all the details. In general, it feels like, yeah, there's the usual, you can do all of these as quantum walks. But I wouldn't be able to tell you what the exact complexity looks like in those cases. But one word to look for there is multi-collisions. And again, it's a different kind of flavor from having like a bunch of separate inputs which collide. If you have like, say, 3 inputs which all give you the same results, then searching for those is a different kind of problem from suppose you have, multiple inputs with their own separate outputs.
One more question. So in the identical subvariant of K round, maybe like even Munzer cipher, maybe K round even Munzer cipher, like how exactly we can apply Simon's algorithm to get the key recovery? Can you briefly sketch the proof of it?
So you're asking about K round Feistel ciphers?
Even Munzer ciphers.
Oh, even Mansour ciphers. Yeah. Okay. Okay. So you have so here you have a cipher where you have like an input. And then you say, I take my key, same size as the input, and you XOR that into the input. And then you apply some, well, people say a permutation, doesn't mean permuting the bits, but you apply some invertible function to this string. And then if you have multiple rounds, you can do like XOR the key in again, and then apply the same permutation or same invertible function, or maybe a different one, and then XOR the key in again, et cetera, and do that for some number of rounds. Now, in this situation, the simplest case to understand is where you have just one round, key coming in once. And in this situation, there's an attack which says, assume that you have quantum access to this function, which means it's like the number 7 at the very end of my slide. It means that the user is willing to encrypt or decrypt data where the data is not just one plain text, but a superposition, so quantum state. So you communicate a quantum state to the encryption, then the secret key is applied. So that means XOR the secret key, then apply the function, then XOR the key again for one round. And in that case, and then give the result back to the attacker as a quantum state. Then in that case, there's a period of something very easily derived from this function. It's something like you take that secret function, including the keys, and then you maybe XOR that with the internal function applied to the input without the keys. I think that's right. And then that function has a period. And then you can apply Simon's algorithm to this complete system, and you end up with the period, the secret key. Now, if you get more rounds, then it starts getting more complicated. And also, if you don't have exactly that full access that I mentioned, then things get more complicated. So, for example, if you have like one, I would say, common situation is you have an input being encrypted and you have a key, but the key is shorter than the input. And what happens is that the input has a constant part, which is where the key is XORed. And it has another part, which is what varies. And that's the input that the user can feed in, like a counter, for example, in counter mode. And then the key is XORed to this part. Then there's an invertible function. Then the key is XORed again. Now, in that situation, that little change that the key is not being XORed to the user input, the key is being XORed to another part of the cipher input, that is enough to stop all of the attacks that are known. And there's some reasons to think that that stops all generic attacks. The reason I'm saying this is a common thing to do, even though Evan Mansour, you have the full width key that you're XORing with the full width plain text and full width ciphertext. The reason I'm saying short is a common situation is, well, this is what Salsa 20 and Cha-Cha 20 do, is they have one piece of the input being the user controlled and another piece being the key is coming in there. And so in that situation, the periodicity, the XORing that Simon is relying on, it just isn't there. You aren't XORing the key with the user controlled part, which is where you have the superposition, the quantum superposition. And then if you were to do multiple rounds, there's some reasons to think that maybe if you have a block size that's not very big, then when you're doing multiple rounds, you get higher security out of Evan Mansour. And in that case, well, the attacks become more complicated. I've seen there's some fascinating recent papers, which are both for Feistel and Evan Mansour, looking at like how can you figure out periodicity in order to be able to apply Simon's algorithm. And there's even some automated search tools now, which are really cool. And those have found rediscovered some old attacks, found some new attacks. And I wouldn't place any bets on how far this is going to go. So I think if you're taking quantum data from an attacker and XORing it with your secret, that's a scary thing to do in general. It's less scary if you have an internal, like if you have multiple rounds, then the attacks get harder because you have some intermediate spot where you're XORing your key with something that's not directly attacker controlled. But just single round Evan Mansour with at the beginning and end where you have the attacker sees the input, sees the output, and that's exactly where you're XORing your key. If you provide quantum access to that, then that's a real problem.
Okay. Follow me. Over to you. You close it. Follow me. Yeah, close it.
Thanks once again, Professor Bernstein. And thank you all for your participation. Okay, have a nice day. Good night.